Introducing quarks. How do quarks work? Quarks are what make the protons. Quark are what make the neutrons. Even astronomers don't convey it good enough to kids, I don't think. The sun is actually making neutrons. And how it does it takes the proton, two up quarks and one down quark. After the Big Bang happened, spread out all these particles, the majority of them were protons. Stars, gravity took over when the sun and stars started fusing protons, hydrogen protons. These are just the nuclei. That's why you can't really call them hydrogens, because you need the electron to make it an atom called. This is just the bare nuclei. They're so high in energy inside stars that the electrons aren't held. So you're binding a proton to a proton. When you smash it together, you know what you get? You get an up becoming more massive to a down. So in order to balance that out, you need to make antimatter, which is in the form of an anti-electron, which is called a positron. So the positron is the first reaction in the sun, is making antimatter. So what you end up with now is a neutron, more massive. I won't go into the mathematics of the charge. It's a +1 on the proton, nothing on the neutron. It's neutral, and it's new, so that worked in. What holds the quarks together are these gluons, so there's 3 for that, 3 for the proton. You get a proton bound to a neutron when you push 2 of the protons together. This is called deuterium, a deuteron. Deuterium is when it's got the electrons, but just the bare nuclei here. This is the first building block to any other element. 2 protons won't stick together. Neutron by itself will decay on average in 12 minutes, I think. So, a proton bound to a neutron all of a sudden is more stable. This is what is happening in the sun right now. Everybody will say, oh, the sun makes helium. Well, in order to make helium, you have to make a neutron first, and then helium is 2 protons. So what will actually happen is you'll have to have 2 of these form. And that's the net reaction, but according to their theory is another proton will hit this, and then 2 of those will get together and kick 2 protons out. And what you end up with is an alpha particle. And the alpha particle is 2 neutrons, 2 protons. Can you see that in there? So that ends up with a net 2+ charge. That's the alpha particle. Why call it the alpha fishy? Okay? Alpha particles, you hear from alpha decay. Well, this is alpha building. So 2, just like 2 protons wouldn't stick together, 2 alpha particles won't stick together very long. So if you have 2 that stick together, before it splits up in a fraction of a second, if another one hits it, you will get carbon 12. This I love because you'll hear that carbon is the most life essential element. Well, it's carbon, nitrogen, and oxygen, technically. But carbon is 3 alpha fishies. And this is what burns me with the astronomers, because they say red stars, oh, they're cold, they're not hot like blue stars. Well, in the core, they are. So you need a higher temperature. Our sun right now is only hot enough to fuse protons into neutrons and then essentially making helium. Later, if it follows the progression, it would form a giant red star after all the hydrogen's used and you're left with all the helium, alpha particles. More gravity would go in. You go from 10 to 15 million degrees to 100 million degrees. Then you can fuse 3 alpha fishies to make carbon 12. So this is a cute little drawing. You got 3 little fishies swimming in a sea. Get it? C for carbon. What's next? Carbon 12, sail the 7 seas. Add 4 alpha fishies, what do you get? Oxygen 16. Notice how these elements are so well known. We breathe oxygen, we eat carbon. Next in the progression is the noble gas neon. Neon is 5 alpha fishes. Now what's cool about the alpha particle thing is alpha decay. I use it as alpha decay is like a alpha fishy jumping out of the nuclear bucket. This is the nucleus. All the alpha particles in there, well, if it's an alpha emitter, it's going to decay by emitting alpha particles. So it's like a fish jumping out of the bucket. Isn't that cute? Now this is what I would think. I think of the show The Jetsons in the 1960s. When little Elroy went to school, kindergarten, he would be studying nuclear physics, wouldn't he? This is what I think our kids should be doing. So now with the cartoon book, I think we can do that. And I think that's going to about do it for the